Hi everyone. So we will start today's lecture. So as usual, we will start from a reviewing of the last lecture. So first, I want to give a relatively quick overview about the motivation about why we study non-interacting system. The first reason is it is usually the simplest starting point, where basically we can analyze our system and get a lot of information. And why it is the simplest one? Because also it is non-trivial. The reason it is non-trivial is because our analysis still contains n degrees of freedom, which means that we are still discussing a system with a macroscopic number of degrees of freedom. However, this is the simplest scenario because the system has no interaction. So that means the partition function is actually factorizable. Because of that, in principle, we should analyze the total partition function. Now, the problem is simplified such that by understanding the single particle partition function and simply raise it to the power of n, or try to make a product of these partition functions of single particle partition functions, we will be able to derive the total partition function. So the non-interacting limit is the simplest one because we can reduce the many-body problem into solving a single particle problem. And that significantly simplify our problem. And my personal experience is that those simplest non-trivial examples are extremely useful when you try to learn a concept, because they basically capture the essential information, and also because they are simple, so we are able to make a lot of progress and build physical intuitions out of them. Okay, so that's the basic motivation why we study these non-interacting systems. So the first one that we encounter is the simple harmonic oscillators. And for simple harmonic oscillators, we first consider the classical one, where we can derive the partition function and get the expectation value of the Hamiltonian or the internal energy E by taking this derivative of the partition function. And the reason that you are able to calculate the expectation value this way can be shown simply if you follow the definition of expectation value of the Hamiltonian, and also knowing that the probability distribution for canonical ensemble is expressed by the Boltzmann factor divided by the partition function. Okay, so once you know how to derive the internal energy, you can take a derivative of your internal energy with respect to the temperature, then you get your specific heat. And from the classical simple harmonic oscillator, we kind of motivate a very generic conclusion that is basically if we try to use the equipartition theorem. And in our lecture, we basically prove the equipartition theorem. And the conclusion for that theorem is that for each quadratic term in the Hamiltonian, you will contribute kBT divided by 2 in the average energy. That is the specific heat will have a contribution of kB divided by 2 for each quadratic term. So that is a very strong conclusion that can be applied to the simple harmonic oscillators or the free particle scenario. Then from the classical harmonic oscillator, we try to ask another question. What happens if we try to consider a quantum oscillator? Similarly, we can try to derive the partition function. and we are able to get the expectation value of our system, the expectation value of the Hamiltonian of our system, which is the internal energy. And the expression we got is like this. And here the n is supposed to be there because we are studying an n oscillator system. So the energy should be proportional with the number of oscillators. And there should be something related to h bar omega, which is the characteristic frequency of the quantum oscillator. And the 1/2 came from the 0-point fluctuation. That is the uncertainty principle of momentum and position. And the last part is the average occupation number of the eigenmodes of the quantum oscillator. And here, this average value of the occupation number is expressed explicitly here. And in the last lecture, I used two notation to denote the same quantity, which is FB or MB. Both of them are representing this particular expression of the average occupation number. Okay, so similarly, once we know what is the energy, we can try to get the specific heat by taking derivative with temperature. Then the expression we got is this one. And the key information we should get is this expression set at the high temperature limit, it will recover the classical limit. Because at this limit, basically, beta h bar omega is a small quantity, so we can expand this beta h bar omega around 0, and eventually these two factors will cancel each other, and the result of the specific heat is basically nkb for a one-dimensional simple harmonic oscillator. And that consists with the prediction given by equal partition theorem. On the other hand, when the temperature is slow enough, that is when it is much slower than the energy quantum, that is basically h bar omega, this is the place where the quantum nature of the system will appear. And it turns out that at this limit, because of this energy gap exists, basically beta h bar omega will be a quantity that goes to infinite. So that means the exponential factor here will dominates. And it turns out that if you do the approximation carefully, the specific heat will be suppressed by this exponential factor. And if we try to plot the figure using the unit of C divided by nkb and the temperature, basically what we found is that at high temperature limit, the specific heat will approach the classical limit. And when the temperature is lower than the so-called Einstein temperature, which is the h bar omega divided by kb, then the specific heat will be suppressed exponentially. And this is the conclusion or the discovery that is made by Albert Einstein back in 1907, which is the time before Schrödinger equation even appears. Okay, so from the classical and the quantum oscillator, we basically can make a simple comparison. The first thing is that we got the frequency from the classical system, and the classical system basically has a continuum spectrum because basically the energy is continuous in the classical system. And when we try to quantize the system, what we found is that now the spectrum is a discrete spectrum, and this discrete spectrum is very regular, that it contains basically equal energy distance. That's the energy gap is basically h bar omega, and every eigenenergy are separated with each other by integer number of integer multiples of this h bar omega frequency. Okay, So that's where we discussed in the last few lectures. And then we have a very quick overview about the idea of Brilliant Zone. And the reason that we want to introduce Brilliant Zone is because when we look at the solid state textbook, or when we are trying to discuss phonon, we usually will have this kind of plot where the horizontal axis is k, which is the wave vector, or the reciprocal lattice vector, and the vertical axis is usually the energy of the corresponding k value. Okay, so the first question is, what is this k? So phonon is a system that usually appears when the system has a periodic structure, for example, in the crystal. So to introduce this idea of Brilliant Zone, we use the simplest 1D example where we arrange these atoms with equal distancing lattice constant A. So in principle, we will have n such atoms, and that will form our system where the system size L is n times A. Okay. So for this kind of system, as we mentioned, since it is a very regular lattice, so we expect the Hamiltonian to be discrete translation only invariant. That is, when we shift our Hamiltonian by a lattice constant A, the Hamiltonian basically is invariant. Okay. So because of that condition, and if we assume that the eigen states is some kind of wave-like wave function, then eventually we will require this condition to be held. That is exponential IgA equal to 1. And here A is the lattice constant and G is the characteristic wave vector correspond to this periodicity A. And it turns out that in order for that to be satisfied, this G needs to be 2 pi divided by A and times the integer, arbitrary integer n. Okay. And then when we study a system that is basically a large system that n is of order 10 to the power of 23, usually we said the boundary condition is not essentially important. So we decide to choose the boundary condition satisfy our need. Basically, we just choose the convenient boundary condition to study our system. So usually, the convenient boundary condition is the periodic boundary condition, which means that the Hamiltonian H will be invariant once you translate the system by a system size L. Okay, so it is very similar with the discrete translation symmetry we just discussed before. So that means that we also have a condition that needs to be satisfied. That is exponential ik times the system size L needs to be 1. So the corresponding reciprocal vector k is 2 pi times some integer m divided by L. And here, because m is n times the lattice constant, the last equality is just a trivial replacement of the system size by the lattice constant. Okay, so now if we try to draw this k and g on the same line, which is the reciprocal space, then those cross marks are the reciprocal vectors that correspond to the g, and these red ticks are basically the k vector that we just discussed. So the most important thing that goes from the continuous translation symmetry to the discrete translational symmetry system is that in the continuous case, the wave vector k and k prime, if they are different by their value, they basically are different. But if you impose the periodic translational symmetry or discrete translational symmetry, then you have a non-trivial equivalence relation. That is, the wave vector k actually is equivalent to k plus g, where g is any of the reciprocal lattice vector. Okay, so the reason that they are equivalent is because when you have a wave and you try to project it to a discrete space, these two wave vector will actually correspond to the same oscillation pattern on this discrete space. And that behavior is called the wave aliasing behavior in our last that is discussed in our last lecture. Okay, so now we know what is K, which is the reciprocal lattice vector, and the corresponding Brillouin zone. Oh, by the way, I forgot to mention one of the important things about the first Brillouin zone. The reason that we only care about the physics that is described within the first Brillouin zone is because whenever there's some point that's outside the Brillouin zone, you can always shift it into the Brillouin zone by subtracting integer numbers of these G vectors. Okay, so that's why usually when you look at the solid state textbook, usually people only describe the physics within the first Brillouin zone. Okay, so that is also the situation when we describe the bands of phonon. Basically, what we plot here is the band structure within the first Brillouin zone. Okay, so for a generic system, usually we will have acoustic phonon and optical phonons. Okay, so because the physics of the two system is the two branches quite different, so we'll just discuss them separately. So the first part is the optical phonon. The optical phonon is basically a band or a branch of energy that is gapped for all the k points. Okay, the energy is basically finite and it is not zero. So if we make a very crude approximation, assuming that the curvature of this band is not really important, and we just flatten it as if it is like what I draw here. In this figure, once we make this approximation, basically the dispersion is independent of k, which means that when we write down the energy as a function of k, it is simply a bunch of harmonic oscillator at different wave vector k, and each one has identical frequency omega, which is independent of k. Okay, so in that case, for this flat bands of acoustic, for this flat band of optical phonon, actually that is the independent and quantum oscillator we just discussed. That is basically we recover the Einstein's model for the phonon mode. Okay, and here you can also do a simple check, because in the first Brillouin zone the region size is 2 pi divided by a, and each wave vector k has a difference of delta k, which is equal to 2 pi divided by L, and because L is NA, so it's 2 pi divided by NA. So you can see that there are actually n modes within this first Brillouin zone. Okay, so so we have a rough idea about what optical phonon is, and basically the Einstein's model can be a good approximation for the optical phonon if the dispersion of the optical phonon is not too large. Okay, then in the last lecture we discussed the acoustic phonon, where which is the lower branch of this plot. Okay, so the detail of the acoustic phonon band actually depends on the system. That is, it might bend a little bit, it might bend a little bit earlier or it might bend a little bit slower, but it doesn't matter. There are some generic feature for the acoustic phonon. One of the most important generic feature is that the dispersion is basically linear nearby the long wavelength limit, which is the small k limit. Therefore, we would like to have some idea about this the implication of this generic feature. Okay, so but before we focus on this generic feature, let's try to ask if we have acoustic phonon band, which is described by EK. How should we write down the partition function for this system? Okay, so as usual, the partition function, because now they are non-interacting, we can use the wave vector k to represent the different modes. So the total partition function will be a product of the partition function at each k mode. Okay, so that's what the first equation, first equality sign means. And then we ask for each momentum or the reciprocal lattice vector k, what is the corresponding partition function? And because for each k, we can have different occupation number for our quantum oscillator. So we need to sum over the Boltzmann factor for the corresponding occupation number nk. So that's why here's the summation of this Boltzmann factor. And we can realize that omega k will be depends on what is the dispersion relation ek. And for each one of the mode, basically, we will have a geometric series that we should solve. So in principle, we can sum this infinite series and then just try to make a product for each of the mode. Then we will get the full partition function of our system. Okay. So as I just described, because this EK in general can be something that's relatively complicated and also have a lot of structure that depends on the detail. So we introduce one important model, which is the Debye model. And the Debye model basically try to capture the two generic feature for the acoustic phonon mode. The first feature is that, as we mentioned, that the energy nearby the small k should be linear. But Debye make a stronger assumption, basically assume that the energy for all the reciprocal vector k should be linear. Okay, so that's the first assumption. Basically, he linearized the band. And the second assumption is by noticing that the classical limit of the oscillators should provide us some results that can be compatible with the equipartition theorem. So Debye make a further assumption that when we sum over the frequency, we should have a cutoff frequency such that when we sum over all the density of states up to this cutoff frequency, we should recover the total degrees of freedom, which is 3n. Okay. So a little bit later, we'll see that condition 2 is actually a reverse engineer process. And the condition 1 actually will lead to some to a very interesting result. Basically, in our last lecture, we try to evaluate what is the expectation value of the Hamiltonian. And after some mathematical manipulation, we get this expression. And the key behavior or the key property for this expression is its dependency on the temperature. It turns out that the expectation value or the internal energy for this system with a linear dispersive mode, the energy will be proportional with T to the power of 4. Okay, that means that the specific heat will have a T cube contribution. And this is a feature related to this generic behavior of the linear dispersive mode. And the second assumption will lead to the classical limit. And the reason is because if we try to write down our expectation value of the Hamiltonian and impose the cutoff frequency, we will find that at a high temperature limit where we can expand this expression, we will find that the expectation value of the Hamiltonian or the internal energy can be written as kBT times this particular integral. So that's the reason why Debye require this term to be 3n, because if it is required to be 3n, basically we get back the result that is predicted by equipartition theorem. So to some extent, the Debye model gets the classical limit, basically C equal to 3n kb, by to some extent reverse engineer the calculation. And it is not really physical. However, the important result is about the low temperature behavior. It is quite useful because it gives us the T cube contribution for the specific heat for a system with linear dispersive bosonic mode. So this is actually a very generic result if we try to combine it with the Goldstone theorem. So the Goldstone theorem, we also have a very brief discussion, basically suggests that whenever you have a spontaneous symmetry breaking of a continuous symmetry, it usually leads to a linear dispersive mode. And that usually gives you the T cube behavior at the low temperature specific heat. So this example is an example specific for the phonon mode, but it can be easily connected with the calculation of photon. To some extent, the history is probably run backwards, that people found the description of photon first, and then Debye tried to incorporate this idea into the phonon system. But the spirit is basically, if we try to start with the Debye model, the only thing that we need to replace is that the specific, not the specific heat, sorry, the velocity of the phonon mode now should be replaced by the speed of light, because for the photon, the energy and the momentum relation is omega equal to ck. And also, there's another important difference between the photon and phonon. Basically, phonon is described by oscillation of matter field, and photon itself is actually gauge degrees of freedom, which means that the polarization is much more constrained. That it turns out that the polarization of photon is only 2, not 3. But in phonon case, the polarization is 3 because you can oscillate in 3 different directions, X and Y and Z. Okay, so that's the little remark that I want to say. And maybe you will ask, like, okay, this seems like a very good example for teaching, but is it going to be useful or relevant for some material? And one of the interesting or exotic phenomena that people study recently is about the quantum spin liquid, which is a highly entangled quantum phase of matter. And in this kind of system, also known as quantum spin ice or the U1 quantum spin liquid on the Pirate core, there's a emergent phenomena, basically the emergent photon. So what does that mean? It means that at the low energy, if we try to describe the system, it will look like a compact quantum electrodynamic theory, which is QED. The most striking phenomena is that it is an insulator and it is a disordered magnetic system, but somehow it contains a non-trivial gapless mode, and that gapless mode corresponds to the artificial photon of this particular QED description. And this artificial photon, because of its gapless nature, will actually lead to a T-cube behavior when you try to measure the specific heat of this system at the low temperature. And so that is this behavior is actually a useful signal if you are looking for some gapless mode with linear dispersion. So if you are interested in the study of quantum spin liquid, there's a review that talk about the history, the theory, and also the experiments. Okay, so at this moment, are there any questions? You should be able to unmute yourself if you have questions. Okay, so I think now we will start with something new. So in our last lecture, we basically discussed the oscillation mode, and we also know when we discuss about the quantum particles, there are two families of quantum particles. One is boson, and the other is fermion. So here we will continue our discussion about statistical mechanics and ask what is the influence of the bosonic nature or fermionic nature to the statistical mechanics description. So here is a very rough idea about the classical particles and the quantum particles. Here I say quantum particles in a it is some kind of quote unquote description. So classical particles is something that is easy to imagine. We just have a bunch of particles sitting somewhere, and they are moving basically in various different directions. Okay, so that's the classical particles. So now, if we consider the case that we actually have a quantum particle, basically the particle, instead of described by a point, it should be described by some kind of wave packet. So it could have some oscillations like this one, or it can be some kind of lump of wave function, and they could have some velocity moving in various different directions. Okay, so the important thing is like how to incorporate this wave function like nature into our description. So the zeroth order question we should ask is, under what situation we should start to consider the wave nature of these quantum particles? And the answer is whenever the wave function overlap is no longer negligible, one should start to consider the quantumness of the system from the wave function point. And from the wave function point of view, it will lead to the idea of quantum statistics, which is what we just discussed about the distinction between bosonic system and fermionic system. Okay, so what exactly is boson or fermion? Like, where did they come from? So the question we should ask is actually quite simple. If we have more than one such particle, like if we are discussing particles, at least we need to have two of them. Okay. Here we always focus on the identical particle. Here, identical particle means that the intrinsic property of these particles should be the same. So what do I mean by intrinsic property? For example, the charge of the particle or the mass of the particle are the intrinsic property of the particles. So, for example, if I'm thinking about one electron and the other electron, they basically share the same charge and they can share the same mass, so they are considered as identical particle. And if I talk about a proton, basically the charge of proton, different protons basically have the same charge, and the mass of the protons are also identical. So so protons can be understood as identical particles. So for identical particles, one important question is, can we distinguish them, or we cannot distinguish them? So in the classical system, usually we can just label the particles according to their paths. What do I mean by that? So if we use the horizontal axis as a time coordinate, and we have two particles that maybe collide with each other, so the particle 1 goes like this and the particle 2 goes like that. Okay, because every point of the particle 1 at every space and time is well defined. So basically we can use a path to label this first particle. And we said that, oh, the particle with this type of path, we call it particle 1. And the particle with this type of path, we said it's particle 2. Okay, so that's the reason why in classical system, even though we are considered identical particle, but those particles are distinguishable. So what went wrong when we consider the quantum mechanics? So suppose we have particle 1 and particle 2 collide. At some point, let's say at the very beginning, particle 1 and particle 2 are far away from each other. So if I draw the wave packet of particle 1 and particle 2, basically those two wave packets does not overlap with each other. So there's no problem that we have a more or less well-defined path. However, when they are colliding with each other, which means that the wave function now has some significant overlap with each other. And from the understanding of the quantum nature of the system, we know that we cannot say where is the particle exactly. We can only describe the probability distribution of the particle. So once they have significant overlap, we basically lose the ability to have a well-defined idea of path. So we no longer is able to say there's a path of that can label to the particle 1, because now path is not a well-defined concept. Okay, so once we start to label the particle 1 and 2 in this way, after the collision, actually we cannot tell whether it is particle 1 2 or particle 2 1. So from the this kind of thought experiments, we must make a conclusion that the probability for identical quantum particles to show up at position x1, x2 must be equal to the probability of these identical particles to show up at x2, x1. Okay, so once we have these physical observables, which is the probability needs to have this property, then we can ask a question: what is the corresponding wave function that can give us this kind of probability description? So one simple way to guess is that we know that probability is related to the norm square of a wave function. So we immediately get the conclusion that if we have a many particle, or in this case, it's a two-particle wave function described by phi x1, x2, the absolute value of this phi x1, x2 needs to be identical with the absolute value of phi x2, x1. Okay. So because of that, we get a conclusion that phi x1, x2 can only differ with phi x2, x1 by a phase. Okay. So here, because I'm not writing everything, so I'm going a little bit fast. So I'll just pause here and see if everybody is okay with the argument. The argument starts with, first, if we are thinking about quantum particles, we lose the idea of path. Once we lose the idea of path, we are not able to distinguish which particle is particle 1 and which particle is particle 2. And the argument suggests that the probability of particle 1, 2 should be equal to the probability of particle 2, 1, okay, in space. And because of that, and because of the probability interpretation of the many-body wave function or two-particle wave function, in this case, we know that the wave function phi x1, x2 can only differ with phi x2, x1 by a phase vector. So if there's no problem, I'll just continue. So there's another very important property, that is this operation that x1 and x2 change position. If I perform this operation twice, it should get back to the original status. That is, if we swap x1 and x2 twice, we get back to the original probability description. So suppose the first condition tells us that phi x1, x2 should be equal to phi x2, x1 up to a phase exponential I theta. Okay. Then if we perform this operation twice, then we got the conclusion that phi x1, x2 should be exponential 2I theta times phi x1, x2. And that leads to the conclusion that this phase vector exponential I theta can only be +1 or -1. And the wave function that is symmetrized is what people call the boson. And the wave function that is anti-symmetrized is what people call it the fermions. Okay. So there's a subtle part that I will not discuss in detail. The important thing is that in our discussion, it seems like the dimensionality is not really important. But it is not true. Actually, dimensionality is extremely important in the study of quantum statistics, especially in the 2D system. In the 2D system, we could have something called anyon. That is basically the swapping of particles will not contribute phase vector that is trivially +1 or -1. And the subtle behavior actually came from the fact that the swap operation actually has some non-trivial structure in a two-dimensional space system. So we will leave it for people to explore this interesting quantum statistics behavior. And in our course, we will basically focus on the simple case where we discuss boson and fermions. Okay. So, all right. So we roughly have an idea about what is boson and what is a fermion. Basically, when we try to swap the coordinates, boson should have a +1 overall phase vector, and fermion should pick up a additional -1 base factor. So in order to have such wave function, we can try to symmetrize or anti-symmetrize the wave function for the two particle system. So here is a very simple example. Suppose we have a bosonic system where we have two particular single particle states, A and B, and we have x1 and x2 represent the coordinates for the first and the second particle. Of course, because we cannot distinguish them, and because they are bosonic, so we require this wave function to have the structure such that when we swap x1 and x2, it pick up a overall +1 factor. And obviously, this expression satisfies this constraint because now we write down the wave function as phi a x1, phi b x2, plus phi a x2, phi b x1. Okay, so the only difference of the first term and the second term is that the x1 and x2 is swapped. And because of that structure, whenever you change the description of x1 and x2, basically what you are doing is basically you just shuffle the first term to the second and the second term to the first. And because the sign in the middle is a sum, we basically will not change the sign once we perform this swap of particles. And for fermionic particles, we basically can play the same trick, but instead of symmetrize our wave function, we can anti-symmetrize it to put a minus sign in the middle. And once you swap the x1 and x2, basically we swap the two terms, but because of this minus sign, there will be an overall -1 factor once we perform the swapping. Okay, so that's the simplest case for two particle fermionic wave function. And here, because of this structure, we notice one thing, that if A equal to B, that is, if the two single particle state is the identical one, we will notice that once we perform the swap, these two factors basically cancel each other. So we basically have no contribution when A equals to B. Okay. So this is the idea of Pauli exclusive principle in this simplest two particle scenario. So we have discussed the phonon and photon. Basically, they are bosons, and those particles can basically stay in the same state because they don't have this Pauli exclusive principle. And the most important example for fermions are the electrons, where the particles cannot stay in the same state. And here, the same state means that the state needs to be specified with all the quantum numbers, including momentum and internal degrees of freedom, such as spins. Okay, so I think we will stop here. And then after 10 minutes, we will continue our discussion about the quantum many particle systems in a more formal fashion. Okay, so hi everyone, we'll start our second lecture. So in the last lecture, actually, we have a very quick overview about what do we mean by boson or fermion. And the task for statistical mechanics is to study a system with n particle. So even though we use the two particle system as an example, I would like to give you a rough idea about how to describe an n particle system in general. Okay, so let's start from understanding of the eigenenergy and eigenvectors for a many particle system. So in order to define a quantum system, you need to define the Hamiltonian and the Hilbert space. So a lot of time we focus on the definition of Hamiltonian, but actually understand the structure of the Hilbert space is also very important. So since we are discussing about a many particle system, so the Hamiltonian H actually is a many particle Hamiltonian. If we are talking about a non-interacting system, which means that we have several particles labeled by I, and each particle is described by a Hamiltonian HI. And there's no interaction. That is, in principle, we should have, if we have two particle interaction, we should have terms like this. But because we are discussing about non-interacting Hamiltonian, terms like that is basically dropped or neglected, or we assume that it doesn't exist. Okay, so that's the first part. And whenever we are discussing a many particle Hamiltonian, the corresponding eigenenergy of this Hamiltonian, basically, if you diagonalize it, you will get two information. One is the eigenenergy, En, and here N just label the corresponding eigenenergy. And you will also get the eigenvector, basically the corresponding eigenvector. I'll use this cat notation. I think you should be familiar with it because that's the standard notation people use in quantum mechanics. So if I try to draw the energy using this vertical axis, so basically we will find that there's a ground state E0, and there might be some first excited state, second excited state. Maybe at some point there was a third excited state and fourth excited state. So you will have a bunch of energies, and these energies are called the many body energy, or the many body energy. The set of these E's are the many body energy spectrum. Okay. So each one of them correspond to a specific eigenenergy of the many body system. And this eigenenergy is actually the total energy for that system for the corresponding eigenvector. Okay. So that's about the spectrum of the Hamiltonian. And here we want to ask a more conceptual question. What exactly is this thing? What is the meaning of this operator? Okay. From this formal expression, it seems like we are just adding a bunch of operator. Okay. So we have write down this type of expression in the free particle system. So let's try to use this example. The Hamiltonian is written as the summation of the total kinetic energy. So if we look at this expression, then we immediately see that for this system, the HI is actually pi squared divided by 2m, which is the corresponding kinetic energy for the ith particle. So what exactly is pi? So this pi means that we are measuring the momentum, but we only measure the momentum of the ith particle. But we have various different particles in our system. For example, we have particle 1 and we have particle 2, but only the ith one is the particle that we care about. So this pi operator now should be defined in this Hilbert space that is formed by this n particle system, should be understood in this fashion. So usually we are lazy, so we just write pi. But a more accurate mathematical expression for this operator actually is this huge expression. Okay. So what does that mean? It means that for the first particle, right here, we actually did not change its behavior. So this operator will basically be an identity operator for the first particle. So it must act trivially to the Hilbert space of the first particle. Similarly, because pi only measures the momentum of the ith particle, the second particle, or this operator, should also act trivially within the Hilbert space of the second particle, and all the way to I-1 particle, and the rest of the particles in the system, including the I+1, etc. It is only the ith particle that this operator pi will act non-trivially to the Hilbert space of the ith particle. Okay. So why it is so? Because the total wave function of this system, to some extent, should be something like this. Let me try to reduce the confusion by this notation. So here the label of 1, 2, and I-1, that's outside of the parent, the angle bracket, represent the index of the corresponding Hilbert space. So this is the expression of the many particle wave function. If we try to use the single particle wave functions phi to express this many particle wave function in this many particle Hilbert space. However, at this moment we should be a bit careful, because we don't really know this expression satisfy the indistinguishability if we try to write it down in this way. And in fact, if we just write it in this fashion, this is the representation for distinguishable quantum particles. So it is not complete. In order to get to the complete description of the indistinguishable quantum particles such as bosons or fermions, we need to do something in order to include indistinguishability.